You're already sleepy.
Remove all the.
All right. So we'll be doing some not exactly new, but I will stop what the optimal control problems which we were discussing for the last 2 days. Okay. So I stated quite a few theorems like dynamic programming principle. Then you can derive from the DPP to HJB. And quickly in 5 minutes I have shown that LQ are linear quadratic regulator. So you will see tomorrow by Shaiju the proofs of DPP in the deterministic case. You will also derive the actually using that to high. So by that time you are now familiar with the terms, and you will see some of the proofs how it is. And probably if he gets time, he will also do the LQR. That will complete the some of the gaps which I have left at the last part of it. But of course, I don't think anybody will prove Pontryagin maximum principle, but that needs much more time. I don't think. That would have been nice to give a proof of Pontryagin, because how the controls are, large perturbations are used in small intervals. It's nice, but then you need an hour or more at least to do that. Then you have to skip it. So what I'm today, the questions which of exact controllability. Again, as I said, this each one you need a kind of semester to get a feeling about it. But I will restrict myself to the standard wave equation, and there are different approaches you may see as you go, but I will see what is called the HUM method. Hilbert, it is called the Hilbert uniqueness method. This is what in the 2 lectures I want to cover. Of course, I will try to give some motivation what the HUM method is all about, but we will start with actually the finite dimensional thing. That's what we are going to do here. So the first hour may be more or less finite dimension, and then I will do wave equation with HUM. Then you will see that it is much more general. Other second order elliptic wave type elliptic equations and fourth order equations, many of the equations you can indeed apply such method. So if you recall the last 4 lectures, basically a control system is just want to recall. A control system consists of some sort of what we call state equations, right? That's what you know it. A state equations, the different interpretation can give. You can view it as an input-output system. Okay, input-output system. What's the input? Input is called basically the control. So state equations will consist of control, and output is your trajectory or state. Trajectory, or you can always call a state of the system. Okay. And state equations can be ODE. That's a kind of finite dimensional situation. ODE, finite dimensional. And the state equations can be determined by PDEs and or other kinds of integral equations. But PDEs can be of different type. It can be of hyperbolic and parabolic. Why I am mentioning is that the approach you need to develop for the hyperbolic equation will be different from the approach you need to apply for the parabolic equation. That comes from that is where the richness of the theory of PDE one has to use, because parabolic equations has its own thing like infinite speed of propagation, smoothing effects. On the other hand, hyperbolic equations have completely orthogonal type of properties like finite speed of propagation. It propagates singularities, develops singularities, and this has very good impact in the notion of controllability. All this, so you may not see the proof, but in the proof eventually these are the things affect the notions of controllability. So immediately, developing one method or one approach to of the controllability may not be immediately suitable for other types of things. So the features you will see, some of them you probably will see here. Okay. And then what is the control system? So the control system is state equations which involve the state as well as the control. And what is the purpose of the whole study? There may be certain objective to study, achieve, objective to achieve. So what we have seen in the last 2 days is one of the objectives is you want to minimize or maximize certain functionals. Minimize or maximize, right? Certain cost functionals or energy functionals or in the different format. That's what we all have seen. And this is what led to what are called the optimal control problems, right? Sometimes you may want to reach certain desired state, desired reach, desired set, a rough notion of what is called the controllability, right? We'll state more for the special systems. Sometimes you may not want to do or may not be possible. You want to stabilize the system. So you use the control for all this. Depending on the control, you will have the state where you want to minimize or maximize, or you have to want to reach somewhere, a desired trajectory, applying the control, you want to reach the trajectory to a particular place, then you have the controllability problem. You may not exactly want to do it, you want to make it stabilizes the system. The system may not be, for example, if you have turbulent flow, etc. That's what the PDE stochastic, Navier-Stokes equation people want to do it. Whenever you have systems which due to its operating parameters create turbulence, and then you want to apply controls so that turbulence are removed. You can see in the usual engines and jet engines and many engines, you will see the projected small things. It removes the drag and removes the kind of thing. So that's a physical way of seeing it, but you want to stabilize the system. Stabilize the system. And this is called the stabilization. All these are connected. I'm sure controllability, and you will see more lectures by Raymond on the topic of stabilization for the Navier-Stokes equations. I hope he will do it. I don't know exactly what he will do, but looking at his things, the work he will do the stabilization. So these are the kind of general things we will be looking at it. And what we have seen is this one about the optimal control problem determined by the state equations which are ODEs. That's what the last 4 lectures you have seen. So I will, to motivate, we will start with the finite dimensional systems. Finite dimensional system. In fact, there was 2 weeks back, there was a 10-day program here on exactly mainly based on finite dimensional controllability at IIST. So those who are attended here, it will be beneficial. How does a finite dimensional system look like? The start was, you want to show some approach, and you want to also show them achieving controllability is not that easy even for finite dimensional system. You need proper conditions. So a linear system look like this, right? This all of you know it. V of ut, and you want to have xt naught is equal to x naught, where x naught is in Rn, right? So A is an n by n matrix, and correspond, even though there will be n trajectory to control, it's not necessary that you have to apply n controls. You will see that example. And it's also necessary that even if you give n controls, you will achieve the controllability. That's also not possible. So in general, B is an n by m matrix with m less than or equal to n. So that indicates that there will be m controls on a system. So this is an n by n system. So as the notion of controllability, given x, suppose you start x1 in Rn. So you can also, there are different types of way of space setting. In the PDE case, you will see. So let's restrict in the, try to understand the easier thing. So does there exist U? Maybe you can space the standard space, you use it. Say T0 to T1 to Rm, such that x satisfies this system star together with x at t1 is equal to x1, you see, or x at t, okay, or t naught to t. Does there exist t? Let's use this. T1 used. What does that have? Once you fix u, so you have an x naught in Rn. Once you fix u, this has a unique solution, it will go. So your x1 may be somewhere else. The issue is that you can choose you can vary your u in a suitable class of functions, control set, so that you have a trajectory passing through that and reaches x1 in time t, capital time t. So that's a terminology. Whatever it is, there may be space settings, etc. In general, this is the notion of controllability. You have a particular space in which you have your initial data and you have your final data. So can you adjust your control so that it reaches that trajectory, reaches there. So it will be the form, any definition of controllability will some sort of variance of this type of thing. Okay, so it's written in a more simpler form. So let's start with an example that such a thing is not always possible, even very simple system. So look at an example. x1 dot is equal to, in R2, so you can say x1 dot is equal to x1 plus u and x2 dot is equal to x2. Okay, how do you write in that form? What is your a here? In this case, a is nothing but 1 0 0 1. And what is your b? B is 1 0. And if you write your x is, I am writing this symbol, but first time x2. So that's your system. Can you see how this system is not able, you will not be able to do a controllability? You get a feeling why this will not be able to control? What do you want? You want both trajectories to reach the desired state, you like it, by suitably adjusting your u. But look at that, the way it's written, this is a decoupled system. The x1 and x2 are separated. So the u will not affect your x2 at all. That means x2 can be uniquely solved here. x2 is fixed, something like x2 naught e power t. You see? So there is only one trajectory for the x2. You cannot change the trajectory at all. So it is already given by a curve. There is no way the u can be adjusted so that the curve changes to pass through the point you like it. So it will not affect. So you may try to think that the controllability is not there because you have applied only one control. But that is not the reason. That's what I am saying to that. That's not the reason. You can achieve controllability even with one control in 2x2 systems. Even n by n systems is possible. So here is another example. You work it out why this is small. It will take time to, if you are seeing the controllability for the first time, it will take some time. But then I have to go much more difficult thing, right? So it's but no other way. So here is a system, x1 dot is equal to x2 and x2 dot is equal to minus x plus u. Can you tell me my a here? Quick.
x1, no?
0, 1.
Very good.
-1, 0.
Very good, right? That's it. That means you are following. Right? It's fine. Still I have the control here. But then now this is no longer a decoupled system. It's a coupled system. But coupled system again doesn't mean that you have the controllability. Only thing is that you cannot rule out there is no controllability. Both are different. In this case, because it is decoupled system, you rule out there is no controllability for the x2 component. But here it may have controllability, it may not have controllability. But then this is a simple system, you can prove this controllability little more quickly. So for, let's see the control. I am saying that this is controllable. And you don't need any technique. Very simple, some small trick will do. How do you do? You can write it as a second order system. If you write x1 dot, it will be x2 dot, and that will be minus x1 plus u. So you will get x1 plus u equal to u. So this system is a first order system corresponding to this second order system. And this is a familiar system of harmonic oscillator, right, which all of you have studied. Okay. And then the idea to prove that one, I am not using any controllability trick. What is my idea? You want to find your x1, x2 in such a way that it should also satisfy your final condition. So you should have your x1 0 is equal to x1 naught and x2 0 is equal to x2 naught, and you also want x1 at t is equal to xt naught and x2 at t is equal to x1t, and you want this to happen, right? That's what you want to do it. So what you do is that you have to know the ways you have to think it as a constraint set. The idea is to look for you forget about the differential constraint, you look for a function which satisfies only this condition. That's not a problem. So you look for a function z, look for z. Do you see that? You can think that these are all two constraints. One is a differential constraint, this is an algebraic constraint. Okay, do you get that point? And look for function which satisfies only algebraic constraint. That may be much more easier than looking for functions which satisfying the differential constraint, and it will be much more difficult to look for both together, both algebraic constraints and differential constraints. And this is, look for a function z such that z at 0 is equal to x1 naught, z prime at 0, you have to also have the feeling that x2 is the derivative of that. So you look at x prime of 0 is equal to x2 naught, z at t is equal to x1t, and z prime at t is equal to x2 at t. That such a function you can construct plenty, because what is that's something like an interpolation, right? You have 4 points are given and you want to find a function passing through that 4 point. You can fit a curve of third degree polynomial or something. So this, I'm not asking that z should satisfy any differential equation. I'm not saying that. So you can find a smooth function z satisfying these points, and that's just this is, since there are 4 points, you can take 3 third degree or something. So that's not a problem. You can plenty of functions. You go and construct today. Okay, you do that, and then what? How do I solve my problem? It's trivial.
That should be twice differentiable. Huh?
Yeah, you can. When you have, I think third degree polynomial is twice differentiable. Suppose so, right? You can. Any kind of functions you can fit. No problem. You can have even C infinity function satisfying that. Yeah, you need, it's better you have a differentiable function twice at least. And then you take x1 equal to z. You take x2 is equal to z prime. Then what is your natural choice of u? Z double prime plus z. Verify this satisfy your controllability. Because already z satisfies this one. So you will have, the way it is defined u is, this is the equation you have to satisfy. You take your, define your u to be like that, and then x1 is satisfies, x2 satisfies all your condition, and you have controllability. So with just one control, you are able to achieve the controllability.
Okay. So there are infinitely many, maybe, right?
Which one?
These controls will be infinitely many because I can connect whatever way I want.
No, not finitely many. There are infinitely many.
Infinitely many only.
No, there are many.
That's what I'm saying. Infinitely many.
Infinitely many. Fine. Yeah, there will be infinitely many. That question we are not coming into it. So the controllability is something you can, it's not trivial. There are systems where you cannot have the controllability. There are systems where you have the thing. Okay. So Actually, in Kalman provided when we are matrices independent of T, he gave a very necessary and sufficient condition of controllability using controllability, Gramian and other things. So there are things. I'm not going to do that. So there is a necessary and sufficient condition for such a system to be controllable. Kalman condition 1960s were that the rank of, this is a necessary if and we are constant matrices AB, right? Shaktivel will help me if I make a mistake. Okay. So the rank of this matrix should be n. If the rank of this matrix is n, is a necessary and sufficient condition for the system to be exactly controllable. I'm not, that approach I don't want to take it, because this is not it is in terms of the dimension, and the dimension, that approach is not good to generalize to PDEs, because PDE is an infinite dimensional analysis. So I don't do that one. So what I want to do is something is I want to tell you some approach is called a variational approach, because in the last 2 days you are in the variational framework, right? So let's do it in that framework of a variational approach. And this is generalizable to PDE, but again I am going to give you something. So you basically get, eventually everything leads to the same thing, but the way you move, the way you look at it varies. So basically eventually at the end of the lecture you get basically 2 approaches, though I promised 1, if I could complete it. So what is called I have an observable system. So I start with so let's recall let's denote this. X dot is equal to Ax plus Bu with x at 0 is equal to x naught, right? So you have that. So I will introduce, and this is a control system, because you have a controlled system. I will also introduce now first a called uncontrolled system. That's minus phi prime is equal to A star of phi. A star is the adjoint of that one. So you need with phi at t. So you have to impose the condition here. Okay, I call it phi t. So given phi t in Rn, you introduce this problem. That's a just a ODE problem. Okay. So this is an uncontrolled system. So from that, let me do a quick calculation.
Related to the control system?
No, nothing. Right now I am not telling. I am going to connect it, and eventually you will see. It's nothing to do. Yeah, of course it's connected with A, the same A. A star is the adjoint of that one. That's the only way it is connected right now. Okay, so you do that.
Very specific or something? That minus sign is very specific or something? That minus of phi dash.
Yeah, that's when you have right system, you use that one. All right. So I do some kind of what you call it in PDE integration by parts, but it is yeah. Let me note. Let me use the same notation. Okay. So you take this phi from here. So if phi t is arbitrary, you take phi and multiply by that one. So you get formally, not formally, that's also true, x dot of phi. This is by definition minus x of phi dot, and then that is equal to minus x of A star of phi. There is something is lost. No.
Oh, that's x is not that.
No. X dot of phi is what? Ax phi. I am missing my control. What do I do? Bu phi. Again, that's just a thing. Okay, here you do the integration by parts. There will be minus x a star phi plus, this is a simple calculation, so you don't have to sleep. Only when you don't follow, you sleep, right? Fine. But this is equal to minus x phi dot yeah, this is plus, right? Yeah, that's a definition. Bu phi. Alright. That's fine. Now I can take this one. Here, what I will get is that d by dt of x phi is equal to Bu phi. This is a very matrix calculate thing, right? So you integrate by parts. What do you do by integration by part? No, you integrate from t to capital T. So you will get x at t, and phi at t is phi t, minus x at 0 is x naught, and phi at 0 is equal to Bu phi. Integral 0 to t. Is that correct? T naught to t if you want it, or 0 to t. Alright? That's correct, right? Yeah, you just integrate this one, you get that. So what does this shows? Yeah, one point I want to forget to tell you, that's a point I want it here. For these finite dimensional systems or linear systems, basically it's more about the linear system. One more controllability, the exact controllability is equivalent to what is called a null controllability. So let me introduce one more notion. Yes. Yeah. What is exact controllability tells you for every x1 endpoint given, you want to find a u such that x at capital T is equal to x1. Null controllability means you want whether everything starting from any point can you reach the trajectory to the origin. So the null controllability is equivalent to there exists u such that x at t is equal to 0. This is a very easy exercise if you want. You can do that. Of course, exact controllability implies null controllability, but the null controllability implies exact controllability is actually trivial. So the idea of doing is that first you look for it y prime is equal to ay, with y at t is equal to y at 0 maybe x naught is equal to, and then look for a solution of the form x equal to y plus z. I think y at t maybe. That you can work out, maybe it's there in the notes also. And then look for a solution. So the exact controllability of x will be equivalent to the null controllability of z. So if you have the null controllability for z, you will get an exact controllability for x. So it's a simple thing. It's not at all difficult. You understand the null controllability? You are looking for the control where the trajectory leads at time t to the origin, not all that point. And this is generally a feature of the linear systems. Non-linear systems is not the feature. Okay? So just work it out, write it. Either you have to, yeah, you have to take it. Yeah, so that's what I'm saying. So it's enough to see the controllability. Now what does this tells you that? If xt is equal to 0, if the system is null controllable, if and only if xt is equal to 0, that's the definition. But xt is equal to 0 implies this term is equal to 0. That means that implies integral x naught phi 0 plus integral 0 to b bu phi equal to 0. Conversely, if this is equal to 0 for all phi coming from here How do you get for all phi? For phi t. Suppose you take arbitrary phi t in Rn and solve this problem, and suppose this is true. So the phi depends on phi t starting with Rn. So for every phi t, you get a phi, and if this is equal to 0 for all phi t, so I can write this is for all phi t. Then if this is 0 for all phi t, implies this is equal to 0 for all phi t in Rn. So that means xt is orthogonal to the every vector in Rn. That means xt is 0. So you have the opposite inequality. So the null controllability is, you can write it as a equivalence of this type of formulation, which is going to be there some sort of optimality condition for the minimization of the functional. That's why this approach is called the variational approach. Yeah, we are going to come that. Yeah, it's not completed. Yeah, it is. That's the thing we want to capture, right? Yeah, you can characterize that. No, but I want to say something more. Okay. So if you, those who are familiar, you know that what minimizes this one. So you are introducing what is called a quadratic functioning. Quadratic functioning. So starting with for phi t hat, phi t in Rn, you define j of phi t is equal to integral 0 to t modulus of b star of phi square plus x star x naught phi 0. Am I right? Yeah. That's it. Maybe half to get it. And then I want to minimize this quadratic functional. Okay. If minimum exists, I am not getting that this is a minimum. That you have seen yesterday, day before yesterday, right? Even for simple functions, you may not have a minimum unless you have the right coercivity property. If you don't have the coercivity, the rest are all fine. Convex continuity, all you may get it, but you may not get the coercivity property in general. So suppose it has a minimum, g phi t hat is equal to, suppose there exists a minimum j phi t. Then what you can do the kind of optimality analysis which I have done. You can vary this once it is a minimum, and then you can see that this minimum will satisfy this condition. If you do an analysis of j phi hat, you vary that phi t hat, exactly what we have done there. So you can do that kind of, basically you are calculating the pressure derivative associated with it, and then you will reach here. So what's the theorem I want to think? So what I will do is that, so let me just state, if you write down its optimality condition, you get this x naught phi 0 plus integral 0 to t b star of phi t hat, no, phi t hat, okay, b star of phi hat, let me, something wrong I have done. So, yeah, it's fine. You can rewrite this in this one more form. Then only this term is same as u acting at b star of phi. Then, okay. So you need that correct form. So you will have b star of phi hat b star of phi is equal to 0. That's what you get. You see? That's fine. So that you have to do a bit of analysis, whatever I said yesterday. That's not difficult. Since this is a minimizer to it, you can vary that phi t hat little bit, and do the same analysis and proceed to get that one. So, but this is in this form. What did we prove? The moment you have some relation in this form, then U is the control for which xt is equal to 0. So, you are producing a control. So, this gives you, the moment you have a relation like that, U gives a control for which you have the null controllability. Xt is equal to 0. So, U equal to what she was trying to command. So, you have your command P hat is the control for which you have your xt is equal to 0. So, the minimizer, so if you have the, a quadratic functional of this form, and if you minimize this equation, this quadratic functional, take the minimum solution, corresponding to this minimum solution, you solve this equation, okay, and take that phi hat and apply your backward with B star, you get your control, which is leading to your system. So, the minimizer gives eventually the solution to your controllability problem. So, what are the advantages of that? Before that, let me write down one more thing, what is called observability inequality. Okay. And that's what you will be seeing in PDE. What is called observability Let me write down observability inequality. What is the system? So, you have your system 2 minus phi prime is equal to a star of phi with phi at t is equal to phi t belongs to Rn. Okay. This system, so you have a control system and you have an uncontrolled system. This is what you have to keep it in mind. You have already have a control system and you have an uncontrolled. The message from here is that you are basically having an uncontrolled system and then you have a minimizer corresponding to an uncontrolled system, if the minimizer exists. Okay. So, because you know already the system is not controllable. So, you cannot expect to have a minimizer this for all the time, because the moment it has a minimizer, it makes the system controllable, null controllable, and in effect it is exactly controllable. So, you definitely need to have some conditions on which this system will have a minimizer. Okay. And that's what we are going to basically say. The system star is said to be observable. We will have more comments about that as we go. Observable in time t positive if there exists c positive such that integral of 0 to t modulus of b star of phi greater than or equal to constant into modulus of phi at 0 square. Okay. So, this is called the observability inequality for this system. Okay, take few seconds before you can proceed. Yeah, first time you may have, it may take some time, but as these things are reasonably easy, at least, easy in the sense that you can follow. There are no hard analysis involved like wave equation, which I am going to soon present. But the feature is what you have to. You can also see that this is actually equivalent to integral of 0 to t b star of phi square greater than or equal to mod of phi t square. This is a feature which you can see, because phi t, if you have start with phi t going Rn, and if you associate the mapping at phi 0, this is the reason is that phi t going to phi 0 is a bounded linear operator which a bounded inverse, which you can prove. That's not this part of the thing. So, using that you can get this, which you can do. Which one? This one. There is a fee zero. That is fee zero. This is for arbitrary fee, for all fee. This is a test function. That's natural. It's something like here. Suppose u is your solution minimizing integral of grade u square. The minimizer will satisfy this condition, right? You see. That's your weak formulation. You get it. Suppose we want to minimize this one, the strain energy. How does that a minimizer? You get that one. So that's what exactly. So it's a test function. This phi is coming at the phi hat. You make a perturbation using phi. Okay. So you use the perturbations and then look for the solution corresponding to the perturbation, subtract it and divide and pass to the limit, which all can be easily done. It's not difficult because it's a final dimensional thing which you can do it. So the vary this one and use that one, and that's a phi you will be getting here. Phi hat will come only here. Yeah, you have to choose something like epsilon pt. Use these perturbations and use basically j of
Minimizer of J, right?
yeah, phi hat t hat is the minimizer of j plus epsilon phi t. This is the procedure we'll do. This is intensely done in PDE. You have to. This is the thing you will be getting. So you have to start with this inequality and proceed further. That's optimal control approach which you do the variational approach. Go and do the smooth cases. Here that's not a problem. You proceed it. Eventually end up with this one because you can also change this to minus and all that. So you don't have any problem.
Here you said that U as this kind of here is the control. So
Sorry. All right. That's true. That's not. It's not the control. Okay. So that is the. So here is a very interesting point I want to note down. It's a kind of thing. So what does this tells you that? You see this, what does it tells you that? This equation, if b star of phi is equal to 0, this will be t. 0 less than or equal to t less than or equal to t. That implies your phi t is equal to 0. This is basically what is called the unique continuation principle. Unique continuation principle. So what does it say that when your system is has this observability estimate, an observable system is observable, and then it satisfies a unique continuation principle. But for finite dimension, that's the difference between when you go from the ODE to PDE. For a finite dimensional system, this condition will also imply this, because in that case you can take half of power of the half of that one. The unique continuation principle will tell you if b star of phi holds power half, the unique continuation principle say that this will be a norm in Rn. Okay, so unique continuation principle produces a norm based on b star, and since it's a finite dimensional, the norm will be equivalent to the standard norm of phi t. So the observability estimate, which is the crucial and more powerful, implies unique continuation principle always like that. But the unique continuation principle implies the observability estimate, and that is in finite dimension. And infinite dimension situation, this is not going to be true. And that's why but one thing you have to see that proving this is actually proving a uniqueness theorem for PDE systems. Okay, it reduces to proving certain uniqueness results. All right. So
Sir, one doubt. Phi that should be Phi0 or that should be Phi t?
this one.
I have a
This is Phi0. Phi t started with the Phi t. According to this observable system, it is something like that. A system is evolving. When a system is evolving, you are not able to understand the state completely. You may be understanding the state a partial information regarding the state. That's what B star does. Okay, so this one tells you that if start with the phi t at some point, when the state moves, you don't have the information of the state fully. But then you have an information about something like B star of phi acting, which you can treat it as a partial information. Observability, that's true. So you are observing something partially, but for a sufficient time. Not you are observing some partial information at one point. What you are observing is that you are observing something continuously for a period. Okay. When you do that one, eventually you are getting your complete information, complete knowledge about the state. So the unique this observability inequality, the power of observability inequality is that if you have observability inequality, it tells you that an observation of your partial information for a time t is enough to get your state of the system completely. That's what it is showing here. You see, this immediately tells you that. So your B star of because there is no observation, there is no state basically. Phi t equal to 0 implies P is identically 0. Okay.
How do you prove? This inequality implies that inequality.
Which one?
This one implies Phi t. How did you declare?
That is, I think you have to prove this. I don't have the right now proof.
I think it must be reversed. I mean, I don't see the.
No, this will imply the phi t going to phi 0.
Continuous, but you get a reverse inequality.
No, you can prove equivalence. I don't have right now the proof. You will be able to get. This should be able to do because it's a finite dimensional system. You have to be able to do that. May not be for the infinite dimensional systems. Okay. Yeah, I know that. But do I have the proof now? No, I may have to prove it. I think this is the point. This will be a bounded linear operator with bounded inverse. Okay, this is a bounded. That's what I said. Bounded linear operator. This is important. The second portion with the bounded inverse. Then only you will get that. You can do that. It may not be difficult, but I don't right now recall. But this fact is true. Okay. Then only you will get that. All right. Yeah. Anything else?
Basically, we substituted Phi0 and Phi t there.
No. You have. That's what he asked. There is something more involved.
From this step to that top step.
Step you have to do this one.
Oh, before okay.
When you have a phi t, the evolution with respect to let me not write a t itself here. Okay. So you have to associate when you have a trajectory moving from here and at time t, where does it reach? Okay. All right. So one more thing in this thing before going to PDE. I don't know how far we can go. So what I want to do is that. So here is what the main theorem now in this here. The system star is observable. That means there is an observability inequality if and only if the control system is controllable. Control system is controllable. Now controllability is enough to prove. So that's it. So I will give you a quick proof, but the feature is what I want to, the feature of this whole program. That a controllability problem, before that controllability problem we reduced basically to an uncontrolled problem. You see, there is no control here, control problem, plus an observation, you do some observation, and plus an observability inequality. Inequality. You see? So that's a thing which an non-control. In PDE, when all this converts into, it's just a pure PDE problem. You don't have to think of there is a control problem at all. So you have the uncontrolled thing, which is like this for this particular case, and then you have an observation. So if you look at eventually the most of the things in the literature, the whole controllability eventually reduces to proving some sort of observability inequality, which is a type of reverse inequality, hence the difficulty. You don't get it. It's not a inequality estimating from above. It's an inequality estimating from below. And that's exactly, you have to do this observation. You see, this is what you have to prove it. Okay. So let me just try to prove this one. Yeah, one way is easy. Suppose observability inequality is true. This way. System is observable. Assume star is observable. Then it's a trivial thing, because if star is observable, yeah, I wrote that thing also needed. That implies that my function j is quasi. That's what it is. This is what we are missing it. That equivalent inequality which we have written with phi t. So that implies immediately your phi t. This is the thing, right? This star of phi square is greater than or equal to phi t square. So if this is true, system is observable, then phi t tends to infinity, implies your b star of phi is infinity, j of phi t will go to 0. That's what the term is appearing in the j. Once you have the j, you already have the continuity and convexity, and this gives a minimizer. And we already seen that once it has a minimizer, the system is controllable. That's the first step we have seen it. Okay. So that implies control system is controllable. This we already proved, right? Once it has a minimizer, control system is controllable. The converse part is also not difficult, but then you need little more. Suppose the system is controllable. Assume system is controllable. Okay, and you have to prove this, right? You have to prove the other inequality. So let me write the inequality with the phi t here. This is what you have to prove it. You have to prove this. You have to prove star, right? To prove star. That's a converse. Suppose this is not true. Suppose star is not true. Suppose star is not true. What can you tell about that? You can produce a sequence Vtk. There exists Vtk such that you can normalize it so that your Vtk is equal to 1 and integral of 0 to t modulus of b star of phi k goes to 0. Okay. From that you can deduce few things quickly. I'm going little fast so that you can do something of PDE also. I want to finish so that I can. From that you can do two things. You can prove modulus of Vt is equal to 1. So you don't have the difficulties of infinite dimension at this stage, because these are all boundedness and all that are all fine. Infinite dimensional spaces you will have difficulty immediately to develop these things, and you can also see that integral of 0 to t b star of phi is equal to square equal to 0. Both these things you can do quickly. So what is phi? Phi is the solution. You have to understand all the time. Phi tk is there. Phi k is the solution of this system corresponding to phi tk. That's what you have to follow. Okay, so you are having a initial or the terminal condition, a family, a sequence of terminal condition. For this you can do that one. The corresponding solutions will fail to do that one. So this is just a contradiction to that one. You have that, and go this one. You have that one. Now you have assumed controllability. You have to prove that the system. We have not used this one. What you have deduced is just if this is not true, what will happen? That's all we have deduced. But the controllability will imply. So you apply controllability. Controllability will imply integral 0 to t that we have already u b star of phi k. For each one you can apply. For each k you can apply, and you get minus x naught phi k 0. This is the inequality. First inequality, what we have proved. The system is controllable if and only if this equality is satisfied. That's the first theorem we have proved. So you apply that for every phi k. So you get that. So you pass to the limit. If you pass to the limit, you get x naught of t0 is equal to 0, which will imply t0 is equal to 0. You can have, there are few small steps left out, which like in PDEs, even there are nothing like small steps, everything will be not trivial. Here you can have, and you can actually prove Pt is equal to the same thing. You don't get it in because once you have phi equal to 0, this will have a 0 solution, and you get phi equal to 0. You see, and this is a contradiction to this fact. Okay. So I thought I will do a little more PDE this hour, but I think we'll have the break and stuff. It's something new, so it may. I don't know. How many of you heard about the exact controllability? Very few.
You don't know, no?
That's optimal. Yeah. That's before this hour. 1 hour before, how many of you? Most of you have not heard about controllability at all? 1, 2, 3, 4, 5. Yeah, no. Yeah. Very few, right? Most of the students are not familiar. Yeah, then I can understand your. That's okay. All right. So we will go to the wave equation soon after this. There are some notes given, so please read. What I stated, the concepts getting may be difficult, but whatever is stated is you can read and understand, because there is it's all about finite dimensional dynamical system of linear system, which you know the theory very well. Once you have x dot equal to ax plus bu, you know how this behaves, everything. So you know how to. So also there are no deep analysis done yet, but introduced in this way so that you have the notion of observability. That's what it is. So what we are going to see is that we are going to get some nice observation for your wave equation. And then you have to prove that inequality, and that's a very hard inequality. You have to have a good knowledge of PDE and the notions like multiplier techniques. So even to state the proof may take 1 hour or 2 hours. So we will not do that. Okay, but we will see the kind of motivation.
The importance will be the operator A star, the structure of the operator.
To get this inequality.
Yeah.
No, not structure. For the finite dimension or PDE?
PDE.
For PDE, it's much more. We do not know what's the kind of B you are getting. So you have a PDE if you write, and in an abstract notion, if you write it in an operator form, how does that, what is that B you are using? So there are various types of controllability. You have a boundary control notion, you have an internal controllability notion. Yeah, so that's what it is. So the B is not easy, right? Here it is fine, but when you write a PDE, how do you write a PDE in this form? I will not go to this aspect. I will not be writing. I will just try to restrict it to the PDE thing. You can also do this kind of more setup, and that way you have to understand more about semi-group theory and all that. And I don't think anybody is covering semi-group. Maybe one lecture you may get it. But so there is a completely operator way of looking at, essentially it is finally the observability inequality. But you can do the same setup in the PDE, but then you will have the systems in infinite dimension. You have to understand what is the meaning of ODE in the infinite dimension setup, and then understand the
machinery, the semi-group theory.
Of that one. But I am going to what present is without semi-group theory. I am going to present just PDE, and PDE is a famous thing called multiplier method. So, but I don't introduce, as I said, the multiplier method. You may need time, at least 1 or 2 hours to derive the inequality. But I will show you how this inequality is coming without introducing A and B, straight away from the PDE. So I will be deriving like an adjoint system and some sort of optimal control. Through the optimal control problem, I will try to give a motivation for the PDE. And you will see what is this phi star. For example, the problem which you are going to see, it is something like dP by d nu. So you are observing your normal derivative across the boundary. So if the normal derivative gives the full information for a long time, you will have the controllability. So you are going to get the control. So it's something different. Because you have to understand how do you convert systems into that form. Maybe some Stokes equations, I don't know, somebody will convert in the operator form or not. I don't know. You will do that way. But then that's a thing.
B star you are telling is difficult in general.
PDE
case domain of B star, that is what you tell.
No. B star is what? What is B there? What is the kind of control you are using? Okay. According to that, it will change, right? Suppose you have an homogeneous term in the boundary. How do you convert that system into that? Or otherwise, you have an internal non-homogeneity. Both are different, right? The way it is converted into an ODE format.
That means the domain and range of B depends as it varies, then everything varies.
But yeah, that is true. That is true. Here, being in Rn, we have the nice metric structure. There it depends on the kind of spaces, your controllability, and all that, and also where you act on the boundary. For example, if you act there's a nice paper. If you have a domain and if you act on the only on some portion, the wave equation will not. See, wave equation has this characteristics and propagation of singularity. So it will not take information everywhere. It may take only information. So you have to apply control in such a way it carries information to that. This is what is called a geometric cortex.
Characteristics should not be trapped.
Characteristic. We will see that. Comments will make. Suppose you have a system here. This is a very nice paper of for PDE. Bardos. Lebo. That's a way. But I don't understand. I don't know how many people can. Somebody can read and tell me it's fine. You have read that too? No. Because it uses microlocal analysis, which I don't know. We know the geometric aspect or Roche. That's a very nice paper. At least the result. So if I don't want to apply control everywhere. All this will come next year. So suppose I apply control only here. And the idea of this hyperbolic nature, that's become the hyperbolic nature. It propagates. The information carries through characteristics, right? That's why it has a nice direction. So if you take an this is the control you are applying. if you look at the ODE, when it is a decoupled system, what happened? The control is not contributing to the second component x2. Okay. So if you similarly, if you carry this information, it has to reach everywhere. So it will get reflected. So if you have a circle, and if I apply only the control here, if I take this diameter here, so if I go here, it will get reflected and come back and it will reflect here. So if I start any point here and if you have this line, it will never touch here. So you don't get controllability. So if you have a controllability and if you want to act something only at the boundary, you have to have a sufficiently big one.
So we have to apply the control everywhere in the domain where we are.
Not necessarily, but that is very expensive.
Yeah.
Because there will be a region will not be accessible to a person. So that's a problem, right? You don't want to do something. You may not be able to reach there to apply control. But you want to act on some place where you, for in a
reactors.
nuclear reactors and pollution of rivers, you don't want to go everywhere in a lake and do it. You want to do it some portion if you like it, and then you should propose. So the Labor's paper gives you a necessary and sufficient geometric condition. I will give in the next class a condition in terms of the another way, which is a sufficient condition. That's, I think, first time done by Leon's. Okay.